Yes. Is this audible? Is it audible? Rakshita, is it audible?
Yes, sir.
Okay. See, in the previous class that we have discussed about this what is that beta minus decay process, right? So now let me discuss about beta plus decay. So see, let me revise that part. So in the morning class we have discussed about the beta minus decay, that is beta minus decay, and emission of electron. Beta minus decay is nothing but emission of electron, right? So here we got that in terms of nuclear mass we are going to define that. So reactant mass should be greater than product masses. It is given by like this. Then even in terms of nuclear atomic mass also we can represent that the same content. So now let us discuss about the beta plus decay. That is second part is beta plus decay. Second part is beta plus decay. Okay. Here this beta plus decay is given by like this. If I treat this as a nucleus with atomic number Z, then mass number A, then that is going to be that new nucleus Y with Z minus 1, where it is going to be plus E0, that is plus 1. Its beta plus is nothing but a electron, this is called as positron. Positron. What do I mean by this positron? Positron is actually a positive electron. Positive electron is defined as positron in this case. If you look at this equation, we get AXZ, that is going to be Y element with a plus Q energy. It's a released energy. Remember, for this process, Q is greater than 0 in this case also. So here also that is Q is positive. Q is going to be greater than 0 only for beta plus decay. For beta plus decay. Okay. That is Q is given by in terms of nuclear mass we can define that as Q is equal to mass of the nucleus with atomic number M, A and Z, then minus the mass of the nucleus with the Z minus 1 with the same mass atomic number A, that is minus Ma. These are for isobars. So this is in terms of nuclear mass. In terms of nuclear mass. Nuclear mass. Okay. Then similarly, you can represent that one in terms of nuclear mass. So if I go through this as Q is greater than 0. So look at this, as Q is greater than 0, I can rewrite this one as, so mass of this A, this is the mass of the reactant, should be greater than mass of the product, Z minus 1 with A, plus times of mass of the electron. Then if you look at this, what I get here, mass of the uh, reactant should be minus times of mass of the A with this Z minus 1. So this should be Z, right? But here it should be Z. Then it should be greater than, that is mass of the electron. Especially this mass of the electron means it's a mass of positron. Mass of positron. So nothing is different. Positron. So only thing is that it's a positive electron. Mass would be similar to, so it is actually equal to mass of electron only, right? Then the same thing if I represent that one in terms of atomic mass, there I get as like this. See here, as you have removed one electron here. As you have removed an electron, then I can replace this one as like this, right? See, if I represent the same thing in terms of atomic mass, if I represent the same thing in terms of atomic mass, so if uh, in terms of atomic mass, in terms of atomic mass, what I get here in terms of atomic mass, so this is going to be m with z times of a, that is going to be greater than, as I told, that is greater than, so mass of z minus 1, this is z minus 1 with atomic mass a, and plus I wrote that is mass of the positron. Okay, keep this one as it is. So anyway, it's a mass of the positron. There is no sign convention for this particularly. Therefore, this. So if I want to convert this one to the atomic mass, what should I write here? I need to add the z number of electrons into it. Then this is completely going to constitute about, what is that? So this is going to constitute about atomic mass. Atomic mass. Okay. Then see, as there are z number of electrons I have multiplied with for the mass. And here, as it is z minus 1, if I want to consider this one as atomic mass, therefore there should be z minus 1 times of mass of the electrons. But according to conservation on the both the side mass of the electrons, so I need to add on the both the side. So here what I get here, this should be like this, right? Just add and multiply, add and subtract one both the side. If I add this z times of mass of the electron, see, as I have added z times mass of the electron, here also I will add z times mass of the electron, z times mass of the electron. Then plus, here already mass of the electron is already there. See, if I want to make this one as this is the atomic mass of the element having z with a. Now this becomes atomic mass because of the addition of the electrons. Here, if I want to treat this one as a mass of the atom, if it is an atomic mass for z minus 1, I need to add z minus 1 electrons. Therefore, add and subtract one electron here. Okay, so conserve this because here z times of me, here also z times of me. So me is already there on the right side according to this equation, right? Therefore, if I add and subtract this mass of electron here, then I am going to write this on 2 times. The same expression can be written as mass of the that nucleus with z with a plus z times of mass of the electron should be greater than mass of the atom with having a atomic number as z minus 1, mass number as a, and thus z minus 1 times of electrons. Z minus 1 times of electrons. Okay. Then plus here 2 times of me, here 2 times of mass of the electron. Here 2 times mass of the electron. Therefore, this is defined as mass of the product, atomic mass of the product, atomic mass of product. Here it's atomic mass of reactant. So this is completely its atomic mass of the resulting nuclei. So this is atomic mass of resulting nuclei. Therefore, this will be 2 times. Then if I rewrite the same thing, see, if I treating them as atomic masses, I will write mass of an element having the z atomic mass number, and A is the mass number. This is for atom. Okay. It's greater than this mass having z minus 1 atomic number with mass number A. This is the atom plus 2 times of Me. Then check, if I rewrite this one like this, the mass of first element minus mass of the resulting element is greater than 2 times of mass of the positron. This is nothing but electron. So this is the condition for beta plus decay. So this is the condition. This is in terms of in terms of atomic masses, for beta plus decay, So this is what the process is. Condition. Moreover, in case of beta minus, what we got the conditions here? In case of beta minus, we got this is going to be greater than 0 by treating that in Z plus 1. Because see here, as it is Z plus 1, here also Z is there, then plus 1 electron is there, therefore that is going to be the total atomic mass of Z plus 1 nuclei. Therefore, in terms of atomic masses, we are going to represent it as it is. It's like this. Clear all? So this is a condition for beta plus decays. Then next part is about separation energy of the last neutron. See, we got the condition and what exactly the beta plus decay. Beta plus decay is nothing but emission of the positron. So always look at these expressions. Look at the conservations of atomic numbers and atomic mass numbers. Atomic number Z, Z minus 1. Conserve this one as Z, we need to add plus 1 here. So therefore total Z in this right side is going to be Z only. Z minus, so that is actually equal to Z minus 1 into this is actually equal to Z minus 1 plus 1 is going to be Z here. So here if you conserve that one, I want to cut Z only. Is this clear all? Then in this case also, this is an electron emission, this is positron emission. So that is defined as a positive electron or beta plus. Done with this? Next concept is separation energy of the last neutron or proton. Next concept is separation energy of last neutron or proton. Separation energy of last neutron or proton. Last neutron or proton. So this is the concept. So what do you mean by separation energy of the last? It is important. So they may almost it is this question based on this part. Question comes in net CSR net. CSR net level questions will be on based on this concept. So it is important. Okay. So what do you mean by separation energy or release of a last neutron or proton? It is actually the energy required to remove the last neutron or proton from the nucleus. Zn is known as separation energy, denoted by Sn. So it's the energy required to remove the last neutron. Energy required to remove last neutron or proton is defined as separation energy. So that is defined as separation energy is represented with Sn or Sp or Sp. So it is the representation of separation energy. Representation of separation energy. Separation energy. Okay. So see, as for example, actually for photons, if you look at for neutrons, what can I write here? For neutrons, see, the separation energy of the last neutron is also equal to energy released when the nucleus captures the neutron get to form a higher isotope. See, this separation energy is equal to its energy released during its capture. Separation energy of the last neutron is also equal to the capturing of same neutron to the nucleus. Therefore, we are going to write this one as if X is the element having Z atomic number and A is the atomic mass number, then when neutron is going to be captured by this nucleus, then energy will be released. The same energy is defined as a separation energy. Separation, whatever the amount of the energy required to separate it, same amount of energy will be released during its capture. Therefore, we are going to rewrite that equation as when a nucleus captures the nuclear neutron, then it is going to get a new nucleus with the atomic number as Z and mass number as A plus 1. A plus 1. Therefore, separation energy Sn is given by this is going to be delta m mass into c square, where the mass difference is going to be Sn. Sn is the separation energy. It is separation energy. For Sn is going to be delta m is nothing but mass of the product minus mass of the reactant. Is that mass of the product minus mass of the reactant? In terms of mass, we are going to have that one as mass of the product and mass of the reactant minus mass of the product. Sorry. Yes, mass of the reactant and mass of the product. Therefore, we can rewrite that one as X with A Z. Sorry, M. If I rewrite that in terms of M, what can I write here? It's a mass with Z, mass with Z. And here O is A plus Mn minus of A with mass with Z. Here this should be Z plus A plus 1. Say this should be mass of the product, that is A with A plus 1 with Z, that is into C square. That gives the total separation energy of that neutron capture. Neutron capture and neutron separation both are same. Energy released. So in terms of binding energy also, it is defined as binding energy, right? This Sn is equal to the binding energy of a atomic number with Z A, mass number as A, minus binding energy of a Z with A minus 1. This is what. 1 minute. Is it audible? This is in terms of binding energy part. Sn is equal to P with A, atomic number as A minus A minus 1. That is the neutron release or neutron capture. Even if you take neutron, if you are going to rewrite the same equation for neutron emission. For neutron emission, what can I write? So if a neutron is getting emitted, how can you write this one as? You see some same A X with Z A. If it emits the what is that? With the atomic number will be same. But here it is going to be, if it emits a neutron, what can I write here? 1, 0. Then what it becomes? It becomes minus 1 here. To conserve this, atomic mass is A minus 1, this is 1. How do you write the energy separation? Separation energy in this case is Sn is equal to is mass X with A minus A X Z minus times if I write this as M. The M with Z minus A minus 1 plus this plus sign of what can I write? 1, 0, 1. So this is the separation. Same thing I have written say there. Okay. Same thing I have written. Only thing is that here it is A plus 1. It is here E. I will write the same equation to compare this one. There what I have written? I have written that Sn is equal to this. Here I had written there M with Z with A. Plus neutron mass, that is mass of the neutron, minus times of A plus 1. And I had written that one as plus 1, right? Yes. A plus 1 with mass number M with A. Is it correct? Nothing. A minus 1 ada, ಇಲ್ಲಿ A ಇಟ್ಟಿನಿ. A ada, ಇಲ್ಲಿ A plus 1 ada. ಅಷ್ಟೇ ಡಿಫರೆನ್ಸ್. ಬಿಟ್ರೆ ಮತ್ತೆ ಇಲ್ಲ. So amount will be same. Plus or minus ಅಷ್ಟೇ change ಆಗ್ತದೆ. Therefore, electron capture and electron emission. So neutron capture, neutron emission both are going to tell us about the separation of the energy by the neutron. Separation energy during the neutron process. The second one is for protons. How can we write the for protons? For protons, we are going to write the same thing as like this. See, for protons, just X is an element. It is having a Z day, and if it emits the proton, means proton is actually defined as a hydrogen atom. Okay, then I can rewrite. See, if there is a new element, if it emits the hydrogen atom as a proton, now we are going to treat this one as a, so we are going to treat this one as proton emission. Proton emission. What should be the atomic number and mass number for this Y? Here see, it is 1, therefore it is minus 1. If here it is 1, therefore it is Z minus 1. That is the thing. How do you write the separation energy in this case? Separation energy Sp is equal to is mass having atomic number as Z minus 1, mass number as A minus 1, plus mass of the proton minus mass with the atomic number A and Z with C square. Isn't it? Or product minus reactant, reactant minus product, doesn't matter. Only if you want to calculate the energy in terms of sign wise, you need, but there is no need to worry about it. It is the energy quantity. If you look at along the quantity, you are going to get this one. Is it clear? So here mass of the proton is taken as mass of hydrogen atom. Mass of hydrogen atom. Clear? Because when you remove the proton, here Z also varies, because Z is equal to the number of protons. Then if you remove the same Z, there is a variation in A. A is equal to Z plus N. And if you remove only one electron from the nucleus or atom, then there will be decrement in Z along with this A also, because A will be decreased by one amount, then atomic number will also be decreased by one amount. So simply they may ask like this. One question also, we'll solve one question here. Simply they may ask like this. Example: calculate the separation energy of the last added. Calculate separation energy. Of last added neutron. So n in helium he is asking. So one neutron ಅನ್ನು helium ಗೆ ಆಡ್ ಮಾಡಿದಾಗ ಎಷ್ಟು ಎನರ್ಜಿ separation energy ಬೇಕಾಗ್ತೈತಿ. ಆಡ್ ಮಾಡೋದಂದ್ರೆ ಏನು, ರಿಮೂವ್ ಮಾಡೋದಷ್ಟೇ equal amount of energy release ಆಗ್ತದೆ. What is that amount is? So generally see, they have given neutron is added for this element. Means see, this helium is a stable one, so we need to add a neutron to it. So stable element is helium with the same 2, but mass number is going to be 3 there. Only we can add to get stable nuclei. Therefore it should be an addition of neutron to the helium atom with mass number 3. Is it clear? So nuclear reactions ಬರಿಬೇಕಾದ್ರೂ ವಿಚಾರ ಮಾಡಬೇಕು. Both stable and unstable. Always ಬರುವಂತ ಪ್ರಾಡಕ್ಟ್ ಸ್ಟೇಬಲ್ ಆಗಿರ್ತದೆ. So keeping that point in mind, we need to write the nuclear reaction. 4. Here there will be a release of energy. Then just you need to rewrite that one as like this. Sn is equal to it's the mass of product. If you take the reactants here, the mass of helium with an atomic number 2, mass number as 3, plus mass of the neutron minus that is mass having atomic number as 2, mass number as 4. That is into c square. Then this gives the total separation energy. Is that clear? Then now, so if in the problem, particularly problem will mention material, he will mention that the masses of each nuclei, that is 3 with m2, so its energy is its mass is going to be 3.0160 AMU. What is this AMU? AMU is nothing but the atomic mass unit. Therefore, similarly, he has given the mass of the neutron as Mn. Mn as so 1.0087 AMU. And similarly, he has given mass of the helium as mass of the helium with atomic mass number as 4. Then that is going to be 4.0026 AMU. Then if you calculate this one like this, let's see, Sn is equal to mass of the helium atom with the mass number 3, that is going to be 3.0160 AMU. Then plus times of mass of the neutron is 1.0087 minus mass of the helium is going to be 4.0026 into c square that is AMU into c square with AMU. Okay. Remember that if you calculate all these values, here I'm going to get that as I think 4.0. I think is it 2? Yes, it is going to be 2 times 2 and 4 and 7. Is that correct? This is correct. Minus times of 4.0026. Then if you take the mass difference in terms of AMU, then I get the Sn is equal to this one. The AMU is the mass difference with c square. Remember, 1 AMU is equal to the amount of the energy that is given by 931 mega electron volt plus c square. So this is the value of 1 AMU. 931 mega electron volt. If I substitute back this in this case, Sn becomes is if you take the difference, we are going to get that as nearly 0.0221, isn't it? 221 into 1 AMU is equal to 931 mega electron volt per c square. 4 into c square already there. 4 c square get cancels. Then I left with that Sn is equal to this. If you multiply this value, I'm going to get nearly this is 20.5 mega electron volt. So this is the energy which is released or energy required to remove the neutron from the helium, to add the neutron to the helium atom. That is the expression for the nuclear reaction, and this is the separation energy released during that reaction. Is that clear? And see, similarly, they have asked one question in NET also. Net and set maybe they have asked in set. I think there's a question. So let us solve this question. Example: the mean momentum of the nucleon inside the nucleus varies as. See, the question is the mean momentum of a nucleon inside a nucleus varies as. So how do you write here? These as first option is e to the power of minus 1. The second option is e to the power of minus 2 by 3. Then third option is e to the power of 1 by 3. Then fourth option is e to the power of minus 1 by 3. Which one is the answer here? They are asking mean momentum. How to calculate the mean momentum? They are asking momentum. What is the relation between momentum and some other things in the nuclear part? Yes. Anyone? So, see, in momentum they are asking. In case of nuclear parts and quantum part, they ask the momentum part, especially for nuclear parts or nuclear nucleons or the atomic particles or nuclear particles, especially that as a nuclear particles. And all these nuclear particles are treated as a quantum particle. So the momentum concept comes in Heisenberg uncertainty principle. Heisenberg uncertainty principle. See, we are going to write the same concept. See, ಇದು ಒಂದು ಪ್ರಾಬ್ಲಮ್ದಾಗ ಹೆಂಗೆ ಇನ್ವಾಲ್ವ್ಮೆಂಟ್ ಮಾಡ್ಕೊಂಡ ನೋಡ್ರಿ. According to uncertainty principle, so according to uncertainty principle, what I get? Principle, what we write, that is delta p into delta x is greater than or equal to h cut by 2. So generally we write this one as delta p delta x or delta p into delta x is nearly equal to h cut. But see here, what is this delta x and delta p is? This is uncertainty in momentum. This is uncertainty in position. So nucleon, they are asking nucleon. So nucleon inside the nucleus. What is the maximum uncertainty in the position of the nucleon in the nucleus? Maximum uncertainty of position of nucleon in the nucleus. Is anyone? If you treat this one as a nucleus, this is a nucleon. Let us take this as a nucleon. So what is the availability of the nucleon within the nucleus? The position availability. So what is the position availability of a nucleon within the nucleus? ಈ ನ್ಯೂಕ್ಲಿಯಸ್ ಎಲ್ಲಿಂದ ಎಲ್ತಾನೆ ಮ್ಯಾಕ್ಸಿಮಮ್ ತಿರುಗಾಡಬಹುದ್ರಿ. ದಿಸ್ ಎಂಡ್ ಹಿಡ್ಕೊಂಡ ಈ ಎಂಡ್ ತನ ತಿರುಗಾಡಬಹುದಾ ನ್ಯೂಕ್ಲಿಯಸ್ ಒಳಗ? What is the distance from here to here? So if I take this one as a center, this is the radius of the nucleus. This is also radius of the nucleus. Once while calculating something, I have taken this delta x as 2r. You know that? Okay. I think ninni class attend ಆದವರಿಗೆ ಅದು ಗೊತ್ತಿಲ್ಲ concept. So with using the same uncertainty, means the availability of the nucleon within the nucleus is always in the range of 2r. Remember that delta x is always equal to 2r. It is taken as 2r, the radius of the nucleus. ಎಷ್ಟು ದೊಡ್ಡದಾಗಿ ನ್ಯೂಕ್ಲಿಯಸ್ ಒಳಗೆ ಓಡಾಡದಪ್ಪ ಅಂತಂದ್ರು ಎಷ್ಟು ಮ್ಯಾಕ್ಸಿಮಮ್ ಡಿಸ್ಟೆನ್ಸ್ ಅದು ಒಂದ್ ಎಂಡ್ ಆಫ್ ದ ನ್ಯೂಕ್ಲಿಯಸ್ ಹಿಡ್ಕೊಂಡು ಇನ್ನೊಂದ್ ಎಂಡ್ ಅಷ್ಟೇ ಇಲ್ರಿ ಅದ್ರ ಮ್ಯಾಕ್ಸಿಮಮ್ uncertainty in the position. Therefore, that is the uncertainty in the position is defined as 2r. Therefore, we can calculate that is delta p. So from this, we can rewrite that as delta p is nearly equal to h cut divided by 2r. is asking dependency of the momentum, mean momentum. That is nothing but an error. Uncertain or uncertainty or mean or whatever it may be, even if it is momentum. How it depends on the nucleus varies as the, it depends on A, they are asking. So we know that R is equal to R, radius of the nucleus varies as A to the power of 1 by 3, where delta P varies as 1 by R. Therefore, I can rewrite that one as delta P is going to vary 1 divided by A to the power of 1 by 3. For delta P or momentum always varies with respect to its mass number as A to the power of minus 1 by 3. That is the answer. See, overall physics knowledge ಇತ್ತು ಅಂತಂದ್ರೆ ಗೊತ್ತಾಗ್ತೈತಿ ಏನ್ ಮಾಡಬೇಕು ಏನಿಲ್ಲ ಅಂತ. ಡೈರೆಕ್ಟ್ ಆಗಿ ಮಾಡಬೇಕು ಅಂತ ಗೊತ್ತಾಗಂಗಿಲ್ಲ. Okay. The kinetic energy of the particle. Kinetic energy of the particle, mean kinetic energy of the particle or nucleon in the nucleus. So the ಹೆಂಗ್ ವೇರಿ ಆಗುತ್ತೆ? Anyone? So question is mean kinetic energy of the nucleon, kinetic energy of nucleon of a nucleus in the nucleus under ನಡೀತದೆ. So in the nucleus varies as in the nucleus varies with the mass number as so mass number as so it is given as A to the power of n. A to the power of n. So what is n value? What is n value? Anyone? Now the kinetic energy, they are asking kinetic energy. You know, what is the variation of how it varies with the atomic mass number A? So what is the value of n here? Anyone? Quickly. 1 by 2. Check it once. If we got that momentum varies as e to the power of minus 1 by 3. Therefore, kinetic energy is given by, what is the relation between kinetic energy and momentum? Kinetic energy is given by P square by 2m, right? 4. The kinetic energy is equal to, which is proportional to P square. Then if you put this P in this case, what I get here? Kinetic energy. Kinetic energy is proportional to A to the power of minus 2 by 3, isn't it? Therefore, n value is minus 0.2.3. 2 by 3 is nothing but 0.66. This is the n value. Next. So there are a lot of problems are there. Solve one problem based on what is this mirror nuclei. So let us take one problem on mirror nuclei. And then we'll go to the next problem. Next concept is nuclear models. Before that, let me solve one problem here. So write down that problem. Just I will rewrite here. Please see. Problem is like this. Silicon 27 with 14 atomic number and aluminium with atomic number 13 with the same 27 atomic mass number are two mirror nuclei having mirror nuclei having identical ground states. Identical ground states. except the changes, except the charges, except the charges, except the charges. If their mass difference, if their mass difference, their mass difference is 6 mega electron volt, 6 mega electron volt. Estimate their radius. Estimate their radius, their radius, neglecting Pn mass difference. Pn mass difference. Yes. Can you do this? So remember, the property of the mirror nuclei is always that the radius will be same. Okay. So we need to remember this property. The property of the mirror nuclei is property of mirror nuclei is that they will have, they have same radius, same nuclear radius. Okay. Yes. Right out. See, already I have given that in terms of mirror nucleus, right? Z1 is greater than Z1, Z1 is greater than Z2. So here let me take Z1 is 40, then Z2 is 13. Okay. So first let us define this here. So Z1 is going to be Z1 equal to N2, then N1 is equal to Z2. Correct? So this is what is the mirror nuclear condition. Next, that Z1 minus Z2 should be always equal to 1 if Z1 is greater than Z2. This is the condition. Mirror nuclear properties. Okay, here I am doing solution. Right. Next, and we know that A1 is equal to A2. So they have already given A1 equal to A2. Look at this. Mirror nuclei available on them. Yes, correct step. How to give its mass difference? I have given that mass difference is equal to 6 mega electron. So how do we define the mass as the mass of the mass difference by neglecting the Pn mass difference? Actually, we read that mass difference of the mirror nuclei is given by, so mass difference of mirror nuclei is given by mirror nuclei number 3 delta m is equal to mp minus mn plus times, what is that? I think that is 2 times of AC into z minus 1 divided by a to the power of 1 by 3 or 2 by 3? 1 by 3. That we have discussed in the morning class. So by neglecting this one, by neglecting this difference, that becomes delta mp minus mn is equal to 0. Then this mass difference delta m becomes only 2 times of AC into z minus 1 divided by a to the power of 1 by 3. Here actually it is a Z means it is Z1. How ಜಾಸ್ತಿ ಇರ್ತದೋ ಅದನ್ನ ತಗೊಂಡಿರ್ತೀವಿ, Z1 ತಗೊಂಡಿರ್ತೀವಿ ಜನರಲ್. ನೋಡ್ರಿ ನಮಗೆ ಏನದ Z1 equal to 1480, Z1 equal to 1480 already then delta m ಏನಂತ ಕೊಟ್ಟಾನವ 6 mega electron. 6 mega electron means 6 into 10 to the power of 6 is equal to 2 times of AC. So what is Z1? Z1 here is 40 minus 1 divided by A. What is this A? A is nothing but 27 whole to the power of 1 by 3. What I get AC here? For AC becomes AC is equal to AC is equal to here we get AC is equal to this this becomes, this part becomes ಏನಾಗ್ತೈತಿ ಇದು 3 ಆಗ್ತೈತಿ, ಇದು 13 ಆಗ್ತೈತಿ, then ಇದು 2 1 2 3 ಆಗ್ತೈತಿ. ಸೊ 3 3 9 ಆಯ್ತು, 9 by 13 ಆಗ್ತೈತಿ ನೋಡ್ರಿ. 9 divided by 13. Is that correct? 9 divided by 30 times into 10 to the power of 6. 9 by 30 into 10 to the power of 6 is equal to AC. ನೋಡ್ರಿ ಒಂದ್ಸತಿ ಇದನ್ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ರಿ ಅಂತ ನಿಮಗೆ 13 ಒಂದ್ಸತಿ ನೀವು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ರಿ ಅಂದ್ರೆ ಮುಂದೆ ನೋಡ್ರಿ ಆಲ್ರೆಡಿ ನಮ್ಗೆ ಗೊತ್ತದೆ AC is equal to ಏನಂತೈತಿ AC is equal to 3 by 5 times 1 by 4 pi epsilon naught E square divided by R naught ಅದ ದೆನ್ ಇಲ್ಲಿಂದ ನಾವೇನ್ ಮಾಡ್ಬೋದು AC ಅನ್ನ ಬ್ಯಾಕ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ರಿ ಇಲ್ಲಿಂದ ನಿಮ್ಗೆ R naught ವ್ಯಾಲ್ಯೂಸ್ ಇದೆ R naught ದಿಂದ R ಅನ್ನ ಹೆಂಗೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡೋರ್ಲಿ how to calculate R here is this R naught or R it's R naught correct it's R naught only AC so how to calculate R naught if you calculate the R naught then you can calculate R because R equal to another R naught into e to the power of 1 by 3 ಐತಿ therefore R naught we can get here R naught is almost ನೋಡ್ರಿ ಏನು ಬೇಕಾಗಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ರೆ ಆಲ್ಮೋಸ್ಟ್ 1.2 1.3 ತನಕ ಬರ್ತದೆ ಎಕ್ಸಾಕ್ಟ್ಲಿ ಇಲ್ಲಿ ಏನು ಬರ್ತದೆ ಆನ್ಸರ್ 1.24 FM ಬಂದಿದೆ R can be calculated as 1.24 fermimeter into what is this e to the power of 1 by 3 e to the power of 1 by 3 is 3 therefore this is going to be ಎಷ್ಟು ಬರ್ತದೆ ನೋಡ್ರಿ I think so 3 2 then 7 then 3 then into 10 to the power of so this is going to be point here into 10 to the power of minus 15 meter that's the answer okay next is this is the answer ita ಮುಂದೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಕೋಬೇಕು is that clear so this is what the problem is ಅದರ ಕೇಳ್ತಾನೆ ಸಿಂಪಲ್ ಕೇಳ್ತಾನೆ ಹಂಗೇನು ಡಿಫಿಕಲ್ಟ್ ಏನು ಕೇಳಲ್ಲ ಮುಂದೆ ಏನೋ ಕೊಟ್ಟಾನ್ರಿ ಇಲ್ಲಿ ಇದೊಂದು ಇಂಪಾರ್ಟೆಂಟ್ ಪ್ರಾಬ್ಲಮ್ ಅದ ಇದೊಂದು ಪ್ರಾಬ್ಲಮ್ ಮಾಡ್ಕೊಟ್ರಿ ಕ್ವಶನ್ ಈಸ್ ಇಂಪಾರ್ಟೆಂಟ್ ಅದ ಪ್ರಿವಿಯಸ್ ಇಯರ್ ಸೆಟ್ ಒಳಗೂ ಕೇಳ್ತಾನೆ ನೆಟ್ ಒಳಗೂ ಕೇಳ್ತಾನೆ ಇದನ್ನು ಎಕ್ಸಾಂಪಲ್ ದಟ್ ಈಸ್ so binding energy of the light nucleus so binding energy of light nucleus that is of a Z with A so ಈ ತರ ಇದ್ದಿದ್ದು ಅಂತ ಒಂದು ನ್ಯೂಕ್ಲಿಯಸ್ is given by approximate formula that is nothing but semi empirical mass formula question is like this is B of binding energy of Z comma A that is nearly equal to 16 times of A minus 20 times of A to the power of 2 by 3 then minus 3 by 4 times of Z square into A to the power of minus 1 by 3 then plus 20 times that is n minus z 30 times n minus z whole square divided by A. So this is what the binding energy formula where n is equal to A minus z where n is equal to capital N is equal to A minus z. We know this. Value of z for the question is the value of z for the most stable isobaries for the most stable isobaries for the most stable isobaries question try ಮಾಡ್ರಿ yes is it audible hello
yes sir
ಹೆಂಗೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀರಿ ಹೇಳ್ರಿ ಇದು ಮೋಸ್ಟ್ ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಏನಂತ ಹೇಳಿದೆ ಮಾರ್ನಿಂಗ್?
ಡಿಫ್ರೆನ್ಶಿಯೇಷನ್.
ಈ ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿನ ಫಸ್ಟ್ ಡೆರಿವೇಟಿವ್ ತಗೋಬೇಕು. ಫಾರ್ ಮೋಸ್ಟ್ ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ ನೋಡ್ರಿ, ಫಾರ್ ಮೋಸ್ಟ್ ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ ಏನ್ ಮಾಡ್ಬೇಕಿಲ್ಲಿ? ಡೋ ಬಿ ಡಿವೈಡೆಡ್ ಬೈ ಡೋ ಜೆಡ್ ಶುಡ್ ಬಿ. ನೋಡ್ರಿ, ಮಾಸರೇ ಕೊಡ್ಲಿ ಅಥವಾ ಎನರ್ಜಿ ಕೊಡ್ಲಿ, ಅದು ಬಂದಿದ್ದ ಅದು ಏನ್ ಬಂದದಲ್ಲ ಅದ್ರದ್ದು ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡ್ಬೇಕೇನು ರೆಸ್ಪೆಕ್ಟ್ ಟು ಜೆಡ್, ದಟ್ ಶುಡ್ ಬಿ ಈಕ್ವಲ್ ಟು 0. ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ರಿ ನಾವು ಇದು ಯಾವ ಜೆಡ್ ಇದೆ ಟೋಟಲ್ ಅದ್ರ ಡಿಫ್ರೆನ್ಶಿಯೇಷನ್ ಮೀನ್ಸ್ ಹಿಯರ್ ಜೆಡ್ ಶುಡ್ ಬಿ ಈಕ್ವಲ್ ಟು ಜೆಡ್ ನಾಟ್. ನೋಡ್ರಿ, ಮೇಲಿನ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡ್ರೆ ಏನ್ ಬರ್ತೈತಿ? ಫಸ್ಟ್ನೇ ಟರ್ಮ್ ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡ್ರೆ ನಂಗೆ ಏನು ಸಿಗಂಗಿಲ್ಲ, 0. ಸೆಕೆಂಡ್ ಟರ್ಮ್ ಆಲ್ಸೋ 0. ಥರ್ಡ್ ಟರ್ಮ್ ನಿಂದ ಸೆಕೆಂಡ್ ಡೆರಿವೇಟಿವ್ ಅದ, ದೇರ್ ಐ ಗೆಟ್ ಸಮಥಿಂಗ್. ನಾಟ್ ಅಬೌಟ್ what is this? Next derivative, that is n minus z. ಇದರಿಂದ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ರೆ ಏನ್ ಸಿಗುತ್ತೆ ನೋಡ್ರಿ ನಿಮಗ. ನೋಡ್ರಿ, ಫಸ್ಟ್ ವಿ ಬಾರ್ ಡೋ ಜೆಡ್ ಫಸ್ಟ್ ಡೆರಿವೇಟಿವ್ 0 ಮಾಡ್ಕೊಂಡೈತಿ ಕರಿ, ದಟ್ ಇಸ್ ಈಕ್ವಲ್ ಟು 0 ತಗೊಂಡ್ರೆ ಫಸ್ಟ್ ಟರ್ಮ್ ಏನ್ ಬರ್ತೈತಿ? ಫಸ್ಟ್ ಟರ್ಮ್ 0, ಸೆಕೆಂಡ್ ಟರ್ಮ್ ಆಲ್ಸೋ 0. ದೆನ್ ಥರ್ಡ್ ಟರ್ಮ್ ನಿಂದ ಏನ್ ಬರ್ತೈತಿ? 3/2 times of z put a to the power of minus 1/3. The next term ನಿಂದ ಏನ್ ಮಾಡ್ಬೇಕ್ರಿ ಇಲ್ಲಿ ನಾವು? ಎಕ್ಸ್ಪಾಂಡ್ ಮಾಡ್ಬೇಕು. ಅದು n ಸ್ಕ್ವೇರ್ ಮೈನಸ್ z ಸ್ಕ್ವೇರ್ ಐತೆ, ಅಲ್ಲಿ ಏನ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಲ್ಲ, ಬ್ಯಾಕ್ n ಮೈನಸ್ z ಐತ್ಲ, ಏನಂತ ಬರಿಬೇಕು ನಾವು? a ಮೈನಸ್ z ಹೋಲ್ ಸ್ಕ್ವೇರ್. ಅದು ಎಕ್ಸ್ಪಾಂಡ್ ಮಾಡಿದ್ರೆ ಏನಂತ ಬರೀತೀರಿ ಇಲ್ಲಿ? is a square plus 4z square minus times of 4az, isn't it? then ಅದನ್ನ ಬ್ಯಾಕ್ ಬರ್ದೈತಿ ಕೊಡಿ ನೀವು. ಸೊ ಎನಿವೆ ಅದು ಸೈನ್ ತಗೊಳ್ಳಿ, ಪ್ಲಸ್ ಡಿವೈಡೆಡ್ ಬೈ a ಅಂತದ, ಇಂಟು ಏನೈತ್ರಿ ಮುಂದೆ? z n ಮೈನಸ್ z ಹೋಲ್ ಸ್ಕ್ವೇರ್ ಐತಿ. ನೀವು ಬ್ಯಾಕ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿದ್ರೆ ಏನ್ ಬರ್ತೀರಿ ಅಲ್ಲಿ? a ಸ್ಕ್ವೇರ್ ಪ್ಲಸ್ 4z ಸ್ಕ್ವೇರ್ ಮೈನಸ್ 4az ಅಂತ ಬರೀತೀವಿ. ಈ ಟೋಟಲ್ ಇದನ್ನ ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡ್ಬೇಕು ನೋಡ್ರಿ. ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡಿದಾಗ ಏನೇನು ಬರ್ತದೆ ಗೊತ್ತಿಲ್ಲ, ಸಾರಿ ಇದನ್ನ ಏನೋ ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡಿಲ್ಲ, ಈ ಪಾರ್ಟ್ ಕೂಡ ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡ್ಬೇಕು. ಏನೇ ಇಲ್ಲಿ 4z ಸ್ಕ್ವೇರ್ ಬರೀತೀನಿ ತೋರಿ. ಓಕೆ, ಇದು ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಅಷ್ಟೇ ಅದು. let us take this a constant, this is b constant. Okay, that is equal to binding energy now. So ಇದನ್ನ ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡ್ರಿ. ಫಸ್ಟ್ ನೇ 0 ಬಂತು, ಸೆಕೆಂಡ್ ಟರ್ಮ್ 0 ಬಂತು, then ಥರ್ಡ್ ಟರ್ಮ್ ಇಂದ 3/2 times of z to the power of minus 1/3 ಬರುತ್ತೆ. ಇಲ್ಲಿಂದ 30 divided by a into 1ನೇ ಟರ್ಮ್ 0, 2ನೇ ಟರ್ಮ್ 8z ಬರ್ತದೆ ಮೈನಸ್ 4a ಬರ್ತದೆ, that is equal to 0. ಫಾರ್ ಇದನ್ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದಾಗ ನಿಮ್ಗೆ z is equal to ಏನು ಬರ್ತದೆ ಗೊತ್ತೇನ್ರಿ? ಟೋಟಲ್ z is equal to ಅಂತ ಬರೋದ್ರ ಅಂದ್ರೆ ಆಕ್ಚುಲಿ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಎಷ್ಟು ಬರೋದು? ಸೊ minus 2z is equal to minus times of a plus a to the power of 2/3 divided by 60 ಬರ್ತದೆ. ಇಲ್ಲಿಂದ ನೀವು ಏನಾದರೂ z ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ರಿ ಅಂತಂದ್ರೆ z becomes ಮೈನಸ್ ಅನ್ನು ಒಳಗೆ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿದ್ರೆ ಏನು ಬರ್ತದೆ? a by 2 minus times a to the power of 2/3 divided by 120. So this is the answer. ನಿಮಗೆ ಯಾವ್ದು a ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ತೀರಿ ಅದ್ರದ್ದು ಮೋಸ್ಟ್ ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ ಸಿಗ್ತೈತೆ. because a will be same na. ಅದಕ್ಕೆ is that clear? ನೆಕ್ಸ್ಟ್, ಸೊ ಈ ತರ ಪ್ರಾಬ್ಲಮ್ಸ್ ಕೇಳ್ತಾನೆ. ಮೋಸ್ಟ್ ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ ಅಂತ ಬಂತ ತಲೆ ಕೆಡಿಸ್ಕೋಬೇಡ, ಅದು ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಇರಲಿ ಅಥವಾ ಮಾಸ್ ಇರಲಿ, ಡಿಫ್ರೆನ್ಶಿಯೇಟ್ ಮಾಡೋದು, ಅದು ಫಸ್ಟ್ ಡೆರಿವೇಟಿವ್ 0 ತಗೋದು, ಅಲ್ಲಿಂದ z ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡೋದು, ದಟ್ಸ್ ಇಟ್. Done with this?
Yes, sir.
Next concept is nuclear models. Nuclear models. ಇದುವರೆಗೂ ಮ್ಯಾಕ್ಸಿಮಮ್ ಕವರ್ ಮಾಡಿ. ನ್ಯೂಕ್ಲಿಯರ್ ಮಾಡೆಲ್ ಒಳಗಡೆ ಒಂದು ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಮಾಡಲು, ಇನ್ನೊಂದು ಶೆಲ್ ಮಾಡಲ್ ಡಿಸ್ಕಸ್ ಮಾಡಿದ್ರೆ ಮುಗೀತದೆ, ಸಿಲೆಬಸ್ ಮುಗೀತೈತಿ. ಇನ್ನೊಂದು ಫಸ್ಟ್ ಟೈಮ್ ಅದ ನ್ಯೂಕ್ಲಿಯರ್ ಮಾಡೆಲ್ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ, ಅದಷ್ಟು ಕವರ್ ಮಾಡು. ನೆಕ್ಸ್ಟ್ ಶೆಲ್ ಮಾಡಲ್ ಒಂದು ನಾಳೆ ಮಾರ್ನಿಂಗು ಅಥವಾ ಈವ್ನಿಂಗ್ ತೊಗೊಂಡು ಅಂತಂದ್ರೆ ನ್ಯೂಕ್ಲಿಯರ್ ಫಿಸಿಕ್ಸ್ ಆಲ್ಮೋಸ್ಟ್ ಮುಗ್ದ. ಅದ್ರ ನೆಕ್ಸ್ಟ್ ಸಮ್ ಪಾರ್ಟ್ಸ್ ಆಫ್ ಪಾರ್ಟಿಕಲ್ ಫಿಸಿಕ್ಸ್ ಡಿಸ್ಕಸ್ ಮಾಡೋದೈತೆ, ಅದು ಮಾತ್ರ ಮುಗೀತು. ಆಮೇಲೆ ಇನ್ನೊಂದು ಬರ್ತೈತಿ ಇಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಮೂವ್ಮೆಂಟ್ ಪ್ರಿಡಿಕ್ಷನ್ ಅಂತ ಬರ್ತೈತಿ, ಆಮೇಲೆ ಎಲೆಕ್ಟ್ರಿಕ್ ವಾಟರ್ಫಾಲ್ ಮೂವ್ಮೆಂಟ್ ಅಂತ ಬರ್ತೈತಿ. ಅವೆರಡು ಡಿಸ್ಕಸ್ ಮಾಡಿದ್ರೆ ಬಿಗ್ ಕಾನ್ಸೆಪ್ಟ್ ಮುಗಿತು. ಓಕೆ, so let us see about these nuclear models. Okay. Any doubt regarding about these separation energy and all those things? Any okay. Next is nuclear model. This nuclear model we are going to study two models, especially mainly two models. Study model. One is liquid drop model. One is liquid drop model. We have the liquid drop model. And second one is shell model. Second one is shell model. Okay. First, let us study about liquid drop model. First one is liquid drop model. Liquid drop model. So this is also called as LDM. So write this one as LD capital M. Model is this model is based on the similarities of a nucleus with a liquid drop. So the assumption is nucleus is assumed as liquid drop. Assumed as liquid drop. Therefore the name is liquid drop model. So in similarities, so it is almost similarities of the nucleus with liquid drop similarities. Okay, similarities. In similarities liquid drop compare ಮಾಡಬೇಕಾದ್ರೆ nucleus na first similarity is density of the liquid drop is independent of the volume. Similarly, density of the nucleus is constant. Liquid drop ಎಷ್ಟು ಬೇಕಾದ್ರೆ ದೊಡ್ಡದಿರಲಿ ಸಣ್ಣದಿರಲಿ ಡೆನ್ಸಿಟಿ ಯಾವತ್ತೂ ಕಾನ್ಸ್ಟೆಂಟ್. ನೀವು ಎಷ್ಟು ಕ್ವಾಂಟಿಟಿ ಯೂಸ್ ಮಾಡತ್ತೀರ ಡಿಪೆಂಡ್ ಆಗಂಗಿಲ್ಲ. ಹೌದಲ್ಲ, density of the liquid drop is independent of its volume. Okay. Density of liquid is independent of its volume. Similarly, density of nucleus is constant. Isn't it? How will notice? Water droplet ತಗೋರಿ ಅಥವಾ ಆಯಿಲ್ ಡ್ರಾಪ್ಲೆಟ್ ತಗೋರಿ, ಎಷ್ಟು ಬೇಕಾದ ವಾಲ್ಯೂಮ್ ತಗೊಂಡ್ರು ಕೂಡ ಅದ್ರ ಡೆನ್ಸಿಟಿ ಸೇಮ್ ಇರ್ತೈತಿ, ಏನು ಫರಕ್ ಆಗಲ್ಲ. ಹಂಗ ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಟೋಟಲಿ ವಾಟರ್ ಲಿಕ್ವಿಡ್ ಫಾರ್ಮ್ದಾಗ ಇದ್ದಿತ್ತು ಅಂದ್ರೂ ಕೂಡ ಅದ್ರ ಡೆನ್ಸಿಟಿ ಆಲ್ಮೋಸ್ಟ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಇರ್ತದೆ. ಅದಕ್ಕೆ ಇದನ್ನ ನ್ಯೂಕ್ಲಿಯರ್ ಮಾಡೆಲ್ಸ್ ಅನ್ನು ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಕಂಪೇರ್ ಮಾಡ್ತೀವಿ. ಇದು ಒಂದು. ಇನ್ನೊಂದೇನು ನೋಡ್ರಿ, ಒಂದು ಲಿಕ್ವಿಡ್ ಸ್ಪ್ರಿಂಕಲ್ ಮಾಡಿದ್ರಿ ಅಂದ್ರೆ ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಸೈಡ್ ಬೈ ಸೈಡ್ ಕೂಡಿದ್ವಿ ಅಂದ್ರೆ ಒಂದು ದೊಡ್ಡ ನ್ಯೂಕ್ಲಿಯರ್ ಒಂದು ವಾಲ್ಯೂಮ್ ಕ್ರಿಯೇಟ್ ಆಗ್ತದೆ. That is by cohesive forces. Therefore, cohesive forces acting in liquid drop. So acting in liquid drop or in a short range liquid drop, similar to nuclear forces acting in the nucleus short range. Even this is for short range possible other. Liquid drop liquid ಸಣ್ಣ droplets side by side ತಂದಿದ್ರೆ ಪಟ್ ಅಟ್ಯಾಕ್ ಆಗ್ತಾವ, ಮೀನ್ಸ್ ದೇ ಅಟ್ಯಾಚ್ ಆಗ್ತಾವ. ಈ ಕೋಹೆಸಿವ್ ಫೋರ್ಸ್ ಆಕ್ಟ್ ಆಗ್ತೈತಿ. ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ತಗೊಂಡ್ರೆ ಅಂದ್ರೆ ಅದಾಗ ಎಲ್ಲ ಪಾರ್ಟಿಕಲ್ಸ್ ಗಳು ಏನಿರ್ತಾವ ಒಂದಕ್ಕೊಂದು ಕನೆಕ್ಟ್ ಆಗಿರ್ತಾವ. ಸಿಮಿಲರ್ಲಿ ನ್ಯೂಕ್ಲಿಯಸ್ ನಾವೇನು ಟ್ರೀಟ್ ಮಾಡ್ತೀವಿ ಇಲ್ಲಿ Nuclear forces are acting on the nucleus. Nuclear forces are acting. Nuclear forces are acting in nucleus. In nucleus for short range. Really could for short range got applicable for short range, isn't it? Therefore, it is a similar to liquid drop. Similarly, latent heat of the vaporization is almost constant in case of liquid as well as binding energy for the nuclear. See, latent heat. If you go to the concept of latent heat of vaporization, vaporization is analogous to constant. Is analogous and similar to constant as in case of binding energy per nucleon of most of the nuclei. This is another one similarity. The operation of the molecule from liquid drop surface is similar to nuclear decay, isn't it? Operation of a molecule from liquid drop surface is similar to nuclear decay. That is nothing but alpha, beta, gamma decays. Hang decay ಆಗ್ತಾವ್ರಿ ನ್ಯೂಕ್ಲಿಯಸ್ ದಿಂದ ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಒಳಗಡೆ ಹೆಂಗ ಒಂದು ಅದ್ರ ಮೇಲಿನ ಸರ್ಫೇಸ್ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಹಂಗೆ ಆಪರೇಟ್ ಆಗ್ತವೆ ಹಂಗೆ ಅಲ್ಫಾ ಬೀಟಾ ಗಾಮಾ ಡಿಕೆ ಆಗ್ತಾವೆ. ದೆನ್ ಇನ್ನೊಂದು ಸಿಮಿಲಾರಿಟಿ ಏನಂದ್ರೆ the fission of liquid drop or the liquid water droplet too, when it gains energy from the outside, similar to nuclear fusion. ನೋಡ್ರಿ ಫ್ಯೂಸ್ ಆದಾಗ ಎನರ್ಜಿ ರಿಲೀಸ್ ಆಗ್ತೈತಿ, ಫಿಷನ್ ಆದಾಗ ಎನರ್ಜಿ ಅಬ್ಸಾರ್ವ್ ಆಗ್ತೈತಿ. ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಹಂಗ ಅದು ಹೊಡಿಬೇಕಾಗಿತ್ತು ಅಂದ್ರೆ ಅದಕ್ಕೊಂದು ಹೀಟ್ ಮಾಡ್ರಿ ಎವಾಪರೇಟ್ ಆಗ್ತೈತಿ. ಹಂಗ ನ್ಯೂಕ್ಲಿಯರ್ ಫ್ಯೂಷನ್ ಏನು ಎನರ್ಜಿಯನ್ನ ಗೇನ್ ಮಾಡ್ಕೋತಿತ್ತು ಒಂದ್ ಕಡೆಯಿಂದ ಔಟ್ಸೈಡ್ ಇಂದ. ಸೊ ಇಟ್ ಈಸ್ ಗೋಯಿಂಗ್ ಟು ಗೋ ಅಂಡರ್ ಫ್ಯೂಷನ್ ಪ್ರೊಸೆಸ್. ಸಿಮಿಲರ್ಲಿ ವಾಟರ್ ಡ್ರಾಪ್ಲೆಟ್ ಅನ್ನ ಎವಾಪರೇಟ್ ಮಾಡೋದ್ರಿಂದ ಏನ್ ಮಾಡ್ಬೇಕು ನೀವು ಹೀಟ್ ಕೊಡ್ರಿ, ಆಟೋಮೆಟಿಕ್ಲಿ ಅಲ್ಲಿ ಏನಾಗ್ತೈತಿ ಮಾಲಿಕ್ಯೂಲ್ಸ್ಗಳು ಎವಾಪರೇಟ್ ಆಗ್ತದೆ. That's why we treat the nucleus as a liquid drop. Main reasons to treat the nucleus as a liquid drop as because its density remains constant. Then second one, cohesive forces will act inside the nucleus like nuclear forces. Then similarly, latent heat of the vaporization is almost constant as in case of binding energy per nucleon for the most of the nuclei. And similarly, evaporation of the molecule from the liquid drop surface. Similarly, nuclear decay ಏನಾಗ್ತೈತಿ alpha beta gamma ದಿಂದ decay ಆಗ್ತದೆ. ನೆಕ್ಸ್ಟ್ ಫ್ಯೂಷನ್ ಆಫ್ ದ ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಫ್ಯೂಸ್ ಮಾಡೋರಿದ್ರಿ ನೀವು ಹೊಡ್ಯಾವ್ರಿದ್ರಿ ಅದನ್ನ ಹೀಟ್ ಕೊಡ್ರಿ ಆಟೋಮೆಟಿಕ್ಲಿ ಎವಾಪರೇಟ್ ಆಗಿ ಹೊಡಿತದ. ಸಿಮಿಲರ್ಲಿ ನ್ಯೂಕ್ಲಿಯರ್ ಫ್ಯೂಷನ್ ಕೂಡ ಹಂಗೆ. ಸೊ by treating this nuclear drop and moreover this binding energy ಅನ್ನು ಡಿಫೈನ್ ಮಾಡಿದೀವಲ್ಲ, ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಈಸ್ ಈಕ್ವಲ್ ಟು ಏನಂತ ಹೇಳಿದೀವ್ರಿ ವಾಲ್ಯೂಮೆಟ್ರಿಕ್ ಎನರ್ಜಿ minus its surface energy e to the power of 2/3 and minus times of its Coulombian forces, that is a into z minus 1 divided by e to the power of plus 1/3 and minus times of its asymmetric part, that is given by a minus 2z whole square divided by a, then minus plus or minus times of varying energy, that is given by e to the power of 3/4. And moreover ಈ ಫಾರ್ಮುಲಾ ಏನದ ಭಾಳ ಅಪ್ಲಿಕೇಬಲ್ ಅದು ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಗಂತೂ ಭಾಳ ಅಪ್ಲಿಕೇಬಲ್ ಅದು. ಅದಕ್ಕೆ ಇದನ್ನ ಜಾಸ್ತಿ ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಮಾಡಲ್ ಒಳಗೆ ಯೂಸ್ ಮಾಡ್ಕೋತೀವಿ. ಇನ್ನೊಂದೇನು ಮೆರಿಟ್ಸ್ ಏನು, Model is able to explain binding energy, atomic mass. This model explains binding energy properly. This model explains binding energy, atomic masses, atomic mass and nuclear mass. Nuclear mass. ಇವಷ್ಟು proper ಆಗಿ explain ಮಾಡೋದು. ಜೊತೆಗೆ this explains nuclear fission successfully. This is the first point. Second point is this model explains nuclear fission successfully. Therefore, these are the merits of liquid drop model. So these are merits of liquid drop model. Merits. So what are the demerits then? Demerits of liquid drop model are first one, that is model is not able to explain magic number. Model is not able to explain magic numbers. Now here the magic number on the next. Then this model is unable to explain nuclear spin and parity. Unable to explain nuclear spin and parity. Next is it is unable to explain magnetic and electric quadrupole. It is unable to explain magnetic and electric quadrupole moments. Magnetic and electric quadrupole moment of a nucleus. Quadrupole moment of nucleus. So ಯಾವುದು liquid drop model compare ಮಾಡಿದ್ರೆ shell model ಇದೆಲ್ಲ explain ಮಾಡ್ತಿದ್ದಾರೆ. Whatever the demerits of the liquid drop model are there, so those demerits will be explained by shell model. So these are the two successful models according to nuclear process explanation as well as nuclear properties. So ಇವಾಗ ಏನ್ ಮಾಡ್ತಾನೆ ಅಂತಂದ್ರೆ ಇಲ್ಲಿ ಒಂದು ಅದ ರೀ ಇನ್ನೊಂದು ನ್ಯೂಕ್ಲಿಯರ್ ಫಿಷನ್ ಅನ್ನ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಕ್ಕಾದ ಭಾರಿ ಹೆಲ್ಪ್ಫುಲ್ ಅದ ಅಂತ ಹೇಳಿದೆ ನಿಮಗೆ. ನ್ಯೂಕ್ಲಿಯರ್ ಫಿಷನ್ ಅನ್ನ ಪ್ರಾಪರ್ ಆಗಿ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡತ್ತಂತೆ. ಈ ನ್ಯೂಕ್ಲಿಯರ್ ಫಿಷನ್ ಅನ್ನ ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಯೂಸ್ ಮಾಡ್ಕೊಂಡು ಏನ್ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತೀವಿ ಅದಕ್ಕೆ ನಾವೇನಂತ ಕರಿತೀವಿ ಅಂದ್ರೆ ಬೋರ್ ವೀಲರ್ ಥಿಯರಿ ಆಫ್ ನ್ಯೂಕ್ಲಿಯರ್ ಫಿಷನ್ ಅಂತ ಕರಿತೀವಿ. So there is a theory to explain using this theory as a liquid drop model. It is Bohr Wheeler theory of nuclear fission. So what is this Bohr Wheeler theory of nuclear fission? See, let us consider this is the nucleus having there are n number of particles. They are bounded by the nuclear force like this. So ಎಲ್ಲಾನು ಬೌಂಡ್ ಆಗಿ ಕುಂತದ. ಎಲ್ಲ ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸಸ್ ಗಳು ಅಟ್ಯಾಕ್ ಆಗತ್ತವ ಇದು ಬೌಂಡ್ ಆಗಿ ಕುಂತದ. If any particle incident on it, this is the incident particle. Okay. Then this nucleus is going to convert into, this is the first stage, that is spherical irtada initially. Okay. Initially spherical irtada nucleus. An incident particle incident on it, then it is going to change its shape as ellipsoidal. It is going to change its shape as ellipsoidal like this. Therefore, this shape of the nucleus is given by now ellipsoidal. Okay. This is first stage A. This is for second stage B. Then after this nucleus goes into dumbbell shape. it is going to convert into dumbbell shape. Wait a second. It is dumbbell shape. Dumbbell shape is going like this, right? So this is dumbbell shape. Then this is defined as dumbbell shape. This is C process. After this, it is going to convert into critical shape. What do you mean by this critical shape? Critical shape is exactly illon part in just to body the part because it is also proton, this is also proton part. The nucleus. So first it is spherical, ellipsoidal, then dumbbell, then after that third stage, D stage is called as critical shape. It comes to fourth stage, that is critical shape. After this, it goes into fission. So after this, it goes into the fission. Then as this is a positive part one part, this is positive part second part. These are the, and moreover positive part ಬಿಟ್ರೆ ಜೊತೆಗೆ ಏನಿರ್ತಾವೆ ಇದ್ರ ಜೊತೆಗೆ ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ನ್ಯೂಟ್ರಾನ್ಸ್ ಇರ್ತಾವೆ. Right? So these two are neutrons because nucleus are separate nucleus ಆಗಬೇಕಲ್ಲ. Then these are fission fragments. So you are doing fission fragments. ವಾಟರ್ ಒಳಗೂ ಹಂಗ ಆಗ್ತೈತ್ರಿ. ವಾಟರ್ ಡ್ರಾಪ್ಲೆಟ್ ಒಂದು ಸಣ್ಣದ ಹನಿಯನ್ನ ಹೋಗದ್ ಬಿಡ್ರಿ, ಒಂದು ದೊಡ್ಡದು ವಾಟರ್ ಡ್ರಾಪ್ಲೆಟ್ ಅದ ಎಲಿಪ್ಸಾಯ್ಡಲ್ ಆಗುತ್ತೆ, ಎಲಿಪ್ಸಾಯ್ಡಲ್ ಡಂಬೆಲ್ ಆಗುತ್ತೆ, ಡಂಬೆಲ್ ಇದು ಆಟೋಮೆಟಿಕ್ಲಿ ಹೊಡಿತದೆ, ಅದು ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್. Similarly, on the same basis, the Bohr-Viral theory of the nuclear fission is defined as like this. Initially, it will be in a spherical, then it converts into ellipsoidal, then it becomes dumbbell, then those nucleons are going to be at the stage of separation, and that stage of separation is defined as critical shape. Then they are going to convert into fission fragment, whereas neutrons. So fission can be induced by some incident particles which carry sufficient energy to disturb them, right? So incident particle will be absorbed by the spherical nucleus, then which is going to be converted into ellipsoidal. Due to the collisions, due to the oscillations in the spherical nucleus, its shape deforms into ellipsoidal. Remember, first stage is that, so the incident particles, incident due to the by sufficient energy, the incident particles should carry the sufficient energy, then they are going to incident on this particle nucleus, then spherical shape is going to absorb the nucleus. Due to the entry of the incident particle, there will be a oscillations in the nucleus. So oscillate agakattavu, akadem oscillate agakattavu. Here nucleons are going to oscillate in the nucleus. Therefore, that shape is going to be ellipsoidal. Then here two forces come into play. One is deforming force, another one is attractive nuclear force. Note, there are two forces will come into play at the stage 3. So at third stage, or at stage 3, or at stage C, two forces come into play. Two forces come to play in the nucleus. Come to play. The first one is deforming force. The second one is attractive nuclear force. It is attractive nuclear force. If the attractive forces are dominant, shape will be dumbbell. So if attractive forces are dominant, then dumbbell shape will be reached, and dumbbell shape will be formed. Oscillations ಆಗೋದ್ರಿಂದ ಏನಾಗುತ್ತೆ, ಡಿಫಾರ್ಮಿಂಗ್ ಫೋರ್ಸ್ ಕ್ರಿಯೇಟ್ ಆಗುತ್ತೆ, ಅಟ್ರಾಕ್ಟಿವ್ ಫೋರ್ಸ್ ಕ್ರಿಯೇಟ್ ಆಗುತ್ತೆ. ಈ ಕಡೆ ಬ್ರೇಕ್ ಆಗಕ್ಕೂ ಟ್ರೈ ಮಾಡಂಗಿಲ್ಲ, ಈ ಕಡೆ ಅಟ್ರಾಕ್ಟ್ ಆಗಕ್ಕೂ ಟ್ರೈ ಮಾಡಂಗಿಲ್ಲ. ಸೊ ಇನ್ ಬಿಟ್ವೀನ್ ಸ್ಟೇಜ್ ಒಳಗೆ ಒಂದು ಟರ್ನಿಂಗ್ ಇರ್ತದೆ, ಕರೆಕ್ಟಾ? Oscillations are very high, then critical stage ಬರ್ತದೆ. Automatically attractive forces ಇರ್ತೈತಿ, damage ಬರುತ್ತೆ, but as because of the entry of the outside particle, then deforming forces start ಆಗ್ತವೆ. Therefore, critical stage ಒಳಗಡೆ oscillations will be very high. At this stage, oscillations will be very high. Oscillations will be high. Will be very high. Therefore, then they are going to create a center at their two positive parts. Next, then it will get break into equal parts the emission of a few neutrons. So these will be emitted neutrons. These will be emitted neutrons. And finally, we can have from heavier nucleus to lighter nuclear fragments create ಆಗ್ತವೆ. Okay. Fission ಒಳಗೆ ಎರಡು ಅದಾವ್ರಿ. This is nothing but a fission. Division of the heavier nucleus into two equal parts or lighter parts is nothing but a fission part. So this is defined as a fission. Heavier nucleus to lighter nuclei. Therefore, fission ಒಳಗೆ ಎರಡು ಪಾರ್ಟ್ ಬರ್ತವೆ. In the case of fission, there are two parts. One is spontaneous fission, and another one induced fission. It is defined as induced fission, induced or stimulated fission. Here we define another one fission part as spontaneous fission. Actually, no bombarding particle is required. No incident particle is required, or bombarding particle. We call that as bombarding particle. No bombarding particle required. No bombarding particle required. Is required. Then second one, here in case of induced particle, bombarding particle is required. So bombarding particle is required. Okay. And see, if the bombarding particle is required, there are two types of bombarding particles. One is by thermal neutrons. So particles can be bombarded with two new particles. That is, one is by thermal neutrons. Then second one is by fast neutrons. Because in both the cases, bombarding particles will have more energy only. So these are energetic particles. Generally, these bombarding particles are energetic particles. Okay. So if you take the thermal neutrons, their energy will be few electron volts. Energy. Thermal neutron. But in case of fast neutrons, their energy will be order of mega electron volt fast neutrons. Then if you go to this by thermal neutrons agittu antandre, if A is odd, if A is odd ittu andre unstable ittu andre idನ್ನ ಯೂಸ್ ಮಾಡಬಹುದು. A is odd is nothing but meaning ಏನು, it's unstable. ಅಲ್ಲಿ ಇದನ್ನ ಯೂಸ್ ಮಾಡಬಹುದು ಯಾವ thermal neutrons. ಬಟ್ ಇದು ಫಾಸ್ಟ್ ನ್ಯೂಟ್ರಾನ್ಸ್ ಅನ್ನು ಎಲ್ಲಿ ಯೂಸ್ ಮಾಡ್ತೀರಿ? if A is odd, if A is even. more stable ಇದ್ದಾಗ more energy ಬೇಕಾಗ್ತದೆ ಡಿವೈಡ್ ಮಾಡಕ್ಕೆ, less stable ಇದ್ದಾಗ less energy ಬೇಕಾಗ್ತದೆ. For example, like uranium 235 ಇದು odd nucleus ಐತಿ. ಇನ್ನೊಂದು thorium 233 ಇದೆ, ಇದು ಕೂಡ odd nucleus. ಸೊ ಇಲ್ಲಿ ನೀವು thermal neutrons with few energy, ಸ್ವಲ್ಪ ಎನರ್ಜಿ ಇದ್ದ ಪಾರ್ಟಿಕಲ್ ಅನ್ನು ಅಟ್ಯಾಕ್ ಮಾಡಿದ್ರು ನಡೀತೈತಿ. in this case fast neutrons ದಲ್ಲಿ ಬಂದ್ರೆ, ಸೊ ಯುರೇನಿಯಂ 238 ನೋಡ್ರಿ, ಇವನ್ ನ್ಯೂಕ್ಲಿಯೈ ಅದು. ಥೋರಿಯಂ 232 ಅದು. ಸೊ ಇವು ನ್ಯೂಕ್ಲಿಯಸ್ಗಳು ಇವನ್ ಅದಾವ. ಅಲ್ಲಿ ಎನರ್ಜಿ ಏನ್ ಬೇಕಾಗ್ತೈತಿ? ಜಾಸ್ತಿ ಬೇಕಾಗ್ತದೆ. here we are going to define a critical energy. A critical energy. What do you mean is critical energy? Anyone? Online actually. Yes. ಹೇಳ್ಬೋದಾ? So what I was asking, energy, critical energy. Critical energy ಅಂದ್ರೆ ಏನಿದು? It's a minimum energy for threshold energy type ಅಂದ್ರೆ ಇದು. ಎಷ್ಟರ minimum energy ಇದ್ರೆ bombarding particle ಗ ನಿಮಗೆ fission ಆಗೋ ಚಾನ್ಸ್ ಅದು. Is called as critical energy. It's energy of the bombarding particle so that it can divide the nuclei. Therefore A ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗ್ತದೆ. ನ್ಯೂಕ್ಲಿಯಸ್ ಆಡ್ ಅದನ್ನು ಇವನ್ ಅನ್ನೋದ್ರ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗ್ತದೆ. ದಟ್ ಈಸ್ ಈ ಕ್ರಿಟಿಕಲ್ ಈಸ್ ಗಿವನ್ ಬೈ ಫಾರ್ಮುಲಾ ಅಷ್ಟದ ನೋಡ್ರಿ 0.89 times e to the power of 1 2 by 3 minus times 0.02 into z minus 1 divided by a to the power of 1 by 3. So ಈ ಕಂಪೌಂಡ್ ಗ ಕ್ರಿಟಿಕಲ್ ಎನರ್ಜಿ ಎಷ್ಟು ನ್ಯೂಟ್ರಾನ್ ಅಟ್ಯಾಕ್ ಮಾಡ್ತಾರೆ ಆಫ್ಟರ್ ಬಂಬಾರ್ಡಿಂಗ್ ಒಂದು ನ್ಯೂಕ್ಲಿಯಸ್ ಅನ್ನು ಅಬ್ಸರ್ವ್ ಮಾಡಿದ ನಂತರ ಎಷ್ಟು ಮಿನಿಮಮ್ ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿ ಅದರಿಂದ ಅದು ಎಮಿಟ್ ಆಗ್ತದೆ ಮೀನ್ಸ್ ಬಂಬಾರ್ಡ್ ಮಾಡ್ಕೊಳ್ತದೆ. That is given by this. It is in terms of mega electron. In terms of mega electron. This is the critical energy ಅಂತ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. ಅಟಾಮಿಕ್ ಮಾಸ್ ನಂಬರ್ ಗೊತ್ತಿದ್ರೆ ಸಾಕು ಡಿಫೈನ್ ಮಾಡ್ಬೋದು. Similarly, ಈ fission ಒಳಗೆ ಎರಡು ಟೈಪ್ ಬರ್ತವೆ. One is symmetric fission, another one is asymmetric fission. This one is symmetric fission, another one is and asymmetric fission. Asymmetric fission. This is asymmetric and symmetric fission. If, for example, in case of symmetric fission, original nucleus breaks into two exactly equal parts. Original nucleus breaks into two equal parts. So that is defined as symmetric fission ಅಂತ ಕರಿತೀವಿ. ಸೊ Z with A ಅಂತ ಹಿಂಗಿತ್ತು ಅಂತಂದ್ರೆ ಇದನ್ನ ಡಿವೈಡ್ ಮಾಡಿದೀವಿ ಅಂದ್ರೆ ಏನ್ ಕೊಡ್ತದೆ ಗೊತ್ತಿರಿ Z/2 A/2 ಹಾಫ್. ಬಿಕಾಸ್ ನ್ಯೂಕ್ಲಿಯಸ್ಗಳು ನ್ಯೂಟ್ರಾನ್ಸ್ ಪ್ರೋಟಾನ್ಸ್ ಹೊರಗೆ ಬಂದು ಅಂದ್ರೆ ಸೇಮ್ ನಂಬರ್ ಆಫ್ ಏದಾಗೂ ಚೇಂಜ್ ಆಗ್ತದೆ. ಸೊ ದಿಸ್ ಇಸ್ ಗೋಯಿಂಗ್ ಟು ಬಿ Z/2 and A/2. ಎಕ್ಸಾಕ್ಟ್ಲಿ ಈಕ್ವಲ್ ಪಾರ್ಟ್ಸ್ ಆಗಿ ಡಿವೈಡ್ ಆಗಿತ್ತು ಅಂದ್ರೆ ಅದಕ್ಕೆ ಸಿಮೆಟ್ರಿಕ್ ಅಂತ ಕರಿತೀವಿ. ಅನ್ಈಕ್ವಲ್ ಪಾರ್ಟ್ಸ್ ಇತ್ತಂದ್ರೆ ಅಸಿಮೆಟ್ರಿಕ್ ಐತಿ. ಜನರಲ್ ಸಿಂಪಲ್ ಅದು. ಸೊ ಅಸಿಮೆಟ್ರಿಕ್ ಮೀನ್ಸ್ asymmetric can I am define manu that is Z with A another atomic number nucleus ittu. So it is going to split into Z1 A1 plus Z2 A2. Then similar ಈ ತರ ಹಿಂಗೆ ಡಿವೈಡ್ ಆಗ್ತಿತ್ತು ಅಂದ್ರೆ ಇಲ್ಲಿ Z1 is not equal to Z2, A1 is not equal to A2. ಸೊ ಆ ಪಾರ್ಟಿಗೆ ನಾನು asymmetric ಅಂತ ಕರಿತೀವಿ. So spontaneous emission tantanas emission agಬೇಕಾದ್ರೆ what should be the condition for that? So ಒಂದು ಪ್ಯಾರಾಮೀಟರ್ ಅನ್ನು ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. spontaneous symmetric spontaneous fission ಆಗಬೇಕಾದ್ರೆ condition for symmetric spontaneous fission. Symmetric spontaneous fission. Symmetric spontaneous fission. Then it should follow that Z square by A should be greater than 44. Z square by A square for any nucleus. If Z square by A square is greater than 44, then it is go under, or it undergoes spontaneous fission. ತಾಂತನ ಫಿಷನ್ ಆಗಬೇಕಾದ್ರೆ ಮಿನಿಮಮ್ ಕಂಡೀಷನ್ ಏನಾಗಿರ್ಬೇಕು ಅದ್ರದ್ದು ಸ್ಕ್ವೇರ್ ಬೈ ಎ ಸ್ಕ್ವೇರ್ ಏನಾಗಿರ್ಬೇಕು ಗ್ರೇಟರ್ ದನ್ ಸ್ಕ್ವೇರ್ ಬೈ ಎ ಶುಡ್ ಬಿ ಗ್ರೇಟರ್ ದನ್ 44. spontaneous emission, symmetric spontaneous emission. Remember, symmetric spontaneous emission ಆಗಬೇಕಾದ್ರೆ ಇದು minimum condition. ಇದು that z square by a square is greater than 15 ಅಂತೆ. At least ಸ್ವಲ್ಪ fission ಆಗಬೇಕಾದ್ರೆ, so for fission to occur, just for fission to occur, ಸ್ವಲ್ಪ at least fission ಆಗಬೇಕಾದ್ರೆ minimum condition ಏನ್ರಿ, if the energy should be greater than 0, ಅವಾಗ energy release ಆಗಿತ್ತು ಅಂದ್ರೆ fission ಆಗಿರ್ತದೆ. Okay, and it should be that the condition of that one is given by z square by a should be greater than or equal to at least 15 ಆಗಿರಬೇಕು. ಇತ್ತಂದ್ರೆ at least ಅಂದ್ರೆ ಏನಾಗುತ್ತೆ, ಅದು fission ಸ್ಟಾರ್ಟ್ ಆಗ್ತದೆ. ಇದಕ್ಕಿಂತ ಕಡಿಮೆ ಇತ್ತು ಅಂದ್ರೆ fission ಸ್ಟಾರ್ಟ್ ಆಗಂಗಿಲ್ಲ. Next, this is what the actually ಹಿಂದೆ ಥಿಯರಿ ಅದ ರೀ, ಟನಲಿಂಗ್ or ಬ್ಯಾರಿಯರ್ ಕ್ರಾಸಿಂಗ್ ಅಂತ ಕರಿತೀವಿ. ಇದು ಬೋರ್ ವೀಲ್ ಏನದು ಬೋರ್ ಅಂಡ್ ವೀಲರ್ ಮಾಡೆಲ್ ಇಂದ ಅದನ್ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಕೊತ ಹೋಗ್ತೀವಿ. ಅದೇನೇನು ಬ್ಯಾಡ್ ಅನ್ಸುತ್ತೆ, ಡೈರೆಕ್ಟ್ಲಿ ನಾವು ಕಂಡೀಷನ್ ಇಟ್ಟು ಚೆಕ್ ಮಾಡ್ಬೋದು. So that is the condition. So this is actually original condition for symmetric spontaneous emission, fission, symmetric spontaneous fission. Okay, ಮೇಲೆ ಉಳಿದೆಲ್ಲ ಪ್ರಾಬ್ಲಮ್ಸ್ ಅದಾವ, ಇದಷ್ಟ ಕಂಡೀಷನ್ ರೀ ಫಸ್ಟ್ಲಿ. Yes, this is what exactly ಅದರ ವ್ಯಾಲ್ಯೂ 44 ಏನಲ್ಲ, ಆಕ್ಚುಲಿ ಅದು 43.3 ಅಂತ ಬರೀತೀವಿ, ಬಟ್ ಜನರಲ್ ಆಗಿ ಬರೀದಿ ಇಷ್ಟೇ. ನೀವು ಕೇಳಿದ್ರೆ ಇದು ಕಂಡೀಷನ್ ಅಂತ ಕೇಳ್ತಾನೆ, ಹೆಂಗೆ ಬಂತು ಎಲ್ಲಿ ಬಂತು ಅಂತ ಏನು ಕೇಳಂಗಿಲ್ಲ. So this is what is about the ನ್ಯೂಕ್ಲಿಯರ್ ಡ್ರಾಪ್ ಮಾಡಲ್. ಡ್ರಾಪ್ ಮಾಡೋದು ಸಿಂಪಲ್ ಭಾಳ ಐತಿ. ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಟೈಪ್ ಅನ್ನು ಟ್ರೀಟ್ ಮಾಡ್ತಾನೆ, ಹಂಗೆ ಬರ್ಕೋತ ಹೋಗ್ತಾನೆ ಅಷ್ಟೇ. ಸೊ ಶೆಲ್ ಮಾಡಲ್ಗೆ ಇಂಟ್ರೊಡಕ್ಷನ್ ಕೊಡ್ತೀನಿ, ಬಿಡ್ತೀನಿ ಇವತ್ತು ಇನ್ನೊಂದು 10 ಮಿನಿಟ್ಸ್ ತಗೋತೀನಿ. ಶೆಲ್ ಮಾಡಲ್ಗೆ ಇಂಟ್ರೊಡಕ್ಷನ್ ಕೊಡ್ತೀನಿ. ನಾಳೆ ಮಾರ್ನಿಂಗ್ ಏನು ಮಾಡೋಣ, ಶೆಲ್ ಮಾಡಲ್ನ ಸ್ವಲ್ಪ ಡೆಪ್ತ್ ಹೋಗುತ್ತೆ, ಅಲ್ಲಿ ಮ್ಯಾಜಿಕ್ ನಂಬರ್ ಡಿಫೈನ್ ಮಾಡೋದು. ಅದು ಶೆಲ್ ಮಾಡಲನ್ನು ಆ್ಯಕ್ಚುಲಿ ನಾವು ಕ್ವಾಂಟಮ್ ಮೆಕ್ಯಾನಿಕಲಿ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ, ಎನರ್ಜಿ ಐಗನ್ ವ್ಯಾಲ್ಯೂ ಬೇಸ್ ಮೇಲೆ. There we are going to consider spin orbital interaction time and total potential ಎಷ್ಟು ಬರ್ತೈತಿ, ಅಲ್ಲಿ ಸ್ಟೇಟ್ಸ್ಗಳು ಬರ್ತಾವೆ ಶೆಲ್ ಮಾಡಲ್ ಒಳಗೆ. ಸೊ ಅಲ್ಲಿ ಎನರ್ಜಿಯನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೊತೀವಿ, ಹಾರ್ಮೋನಿಕ್ ಆಸಿಲೇಟರ್ ಅಂತ ಟ್ರೀಟ್ ಮಾಡ್ಕೊಂಡು ಶೆಲ್ ಮಾಡಲನ್ನು ಒಂದು ಹಾರ್ಮೋನಿಕ್ ಆಸಿಲೇಟರ್ ಅಂತ ಟ್ರೀಟ್ ಮಾಡಿ ಅಲ್ಲಿ ಎನರ್ಜಿಗಳನ್ನ ಸ್ಪ್ಲಿಟ್ ಮಾಡ್ಕೊತೀವಿ. ಸ್ಪಿನ್ ಪ್ಯಾರಿಟಿ ಪ್ರೆಡಿಕ್ಷನ್ ಅಂತ ಬರ್ತೈತಿ, ದೆನ್ ಅಲ್ಲಿ ಪೇರಿಂಗು ಬರ್ತದೆ, ದೆನ್ ಅಲ್ಲಿ ಇನ್ನೊಂದು ನಾರ್ದಿಯನ್ ಮತ್ತೊಂದು ಬರ್ತೈತಿ, ನಾರ್ದಿಯನ್ ರೂಲ್ ಅಂತೇಳಿ. ನೆಕ್ಸ್ಟ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಮೂಮೆಂಟ್ ಪ್ರೊಡಿಕ್ಷನ್ ಒಂದು, ಆಮೇಲೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಕ್ವಾಡ್ರಾಪೋಲ್ ಮೂಮೆಂಟ್ ಒಂದು ಡಿಫೈನ್ ಮಾಡಿ. ಬಟ್ ಅದಕ್ಕಿಂತ ಮೊದಲ ಲೆಟ್ ಮಿ ಗಿವ್ ಅ ಸ್ಮಾಲ್ ಇಂಟ್ರೊಡಕ್ಷನ್ ಟು ಶೆಲ್ ಮಾಡಲ್ ಅಷ್ಟು ಹೇಳಿ ಬಿಡ್ತೀನಿ. ಓಕೆ, ಶೆಲ್ ಮಾಡಲ್ ನ್ಯೂಕ್ಲಿಯರ್ ಮಾಡಲ್ ಡ್ರಾಪ್ ಮಾಡಲ್ ಒಳಗೆ ಇಷ್ಟ ಐತ್ರಿ, ಭಾಳ ಅಂತದ್ದು ಏನಿಲ್ಲ. ಅಂತಾನೆ ಫಿಷನ್ ಆಗಬೇಕಾದ್ರೆ ಫ್ಯೂಷನ್ ಆಗಿ ಟ್ರೀಟ್ ಮಾಡತ್ತಿದ್ವಿ ಅಂದ್ರೆ ನ್ಯೂಕ್ಲಿಯಸ್ನ ಏನಾಗ್ತದೆ ಅಲ್ಲಿ ಇಟ್ಟೋದು. ಓಕೆ, ಸೊ ಶೆಲ್ ಮಾಡಲ್ ಜಸ್ಟ್ ಇಂಟ್ರೊಡಕ್ಷನ್ ಕೊಡ್ತೀನಿ, ನೋಡ್ರಿ ಒಂದು ಸ್ವಲ್ಪ. ಒಂದು ಕಂಡೀಷನ್ ಏನ್ ಬಿಟ್ಕೊಂಡ್ಬಿಡ್ರಿ, ಇದು ಹೆಂಗೆ ಬಂತು ಏನು ಬಂತು ಈಗ ಸದ್ಯಕ್ಕೆ ಏನು ಬೇಡ, ಅಷ್ಟೊಂದು ಜरूरत ಇಲ್ಲ. ಮತ್ತೆ ಅದನ್ನ ಥಿಯರಿ ಸ್ಟಡಿ ಮಾಡ್ಬೇಕು, ಅಲ್ಲಿ ಕೆಲವೊಂದಿಷ್ಟು ಕಾನ್ಸೆಪ್ಟ್ ಅದು, ಟನಲಿಂಗ್ ಪ್ರೊಸೆಸ್ಸು, ಇನ್ನೊಂದು ಬ್ಯಾರಿಯರ್ ಫಿನಾಮಿನಾ ಅಂತ ಏನೇನು ಇದಾವೆ. ನೆಕ್ಸ್ಟ್ ಮಾಡಲ್ ಶೆಲ್ ಮಾಡಲ್. ಇದ್ರ ಐಡಿಯಾ ಏನು ಹೆಂಗೆ ಅನ್ನೋದು ಅಷ್ಟೇ ನೆನ್ಪಿಟ್ಟು ಸಾಕು. ಇಲ್ಲಿ ಶೆಲ್ ಮಾಡಲ್ ಇಂಪಾರ್ಟೆಂಟ್ ಇದೆ, ಜಾಸ್ತಿ ಕೇಳಿದ್ರೆ ಇದ್ರೆ ಕೇಳ್ತಾನೆ. This model is based on some assumptions. Following assumptions. Based on following assumptions. Following assumptions. And really following assumptions in a shell model. First thing is that both protons and neutrons have freedom of motion within the nucleus. See, both protons and neutrons neutrons have freedom of motion within the nucleus. Motion within the nucleus. Within the nucleus. That is the first assumption. Second, flow free movement. Nucleons ಅಂದ್ರೆ ಇಲ್ಲಿ protons and neutrons of nucleons ಅಂತ ಕರೀತೀವಿ. Nucleons inside the nucleus are arranged in different state. So nucleons inside nucleus are arranged in different states. Just like electrons in arranged in atomic system. Atomic system ಅಂದ್ರೆ ಏನು? electrons ಗಳು first order second order means higher order ಒಳಗಡೆ ಅಥವಾ orbitals ಒಳಗಡೆ ಹೆಂಗ್ ಅರೇಂಜ್ಮೆಂಟ್ ಆಗ್ಯಾವಲ್ಲ, ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಏನಂತ ಮಾಡ್ತಾನೆ ಶೆಲ್ ಮಾಡೆಲ್ನಾಗ ಡಿಫರೆಂಟ್ ಎನರ್ಜಿ ಲೆವೆಲ್ ವೈಸ್ ಅರೇಂಜ್ಮೆಂಟ್ ಮಾಡ್ಕೊಂಡಾವ ಅಂತ ಹೇಳ್ತಾನೆ. ನೆಕ್ಸ್ಟ್, each nucleon move in a average field created by all other nuclei. ನೋಡ್ರಿ, each nucleon move in an average field created by all other nucleons. Then last fourth assumption, each nucleon has two types of motion. One is orbital, another one is spin motion. Assumption: each nucleon have two types of motion. One is spin motion, another one is orbital motion. So this is the assumption, orbital motion. Then they also have different system of orbit around the center of the mass of the nucleus. It is nothing but different states. So they also have different system of orbit around. They have different system of orbit around the center of mass of the nucleus. Around the center of mass of the nucleus. And fifth point is, cells are regarded as field. The cells are regarded as field when they contain specific number of neutrons and protons. The cells are cell model ಅಂತ ಹೆಸರು ಬಂದಿದೆ ಅಂದ್ರೆ different orbits ಗಳಿಗೆ ನಾವು cells ಅಂತ ಕರಿತೀವಿ. Cells are regarded as field when they contain specific number of neutrons and protons. Specific ಈಗ ನಾವು ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ s orbital p orbital ಅಂತ ಹೆಂಗ್ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ ಆ ತರ specific number of protons and neutrons. Then next, number of nucleons in each cell is limited by Pauli principle. ಹೆಂಗ್ ನಾವು ಪ್ರತಿಯೊಂದು ಆರ್ಬಿಟಲ್ ನಾಗ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಗಳನ್ನ ಲಿಮಿಟ್ ಮಾಡ್ಕೊತೀವಲ್ಲ, ಹಂಗ number of nucleons in each cell is limited by Pauli principle. So Pauli principle. These are the assumptions. Actually, ನೋಡಾಕಂದ್ರೆ ಲಿಕ್ವಿಡ್ ಡ್ರಾಪ್ ಮಾಡಲ್ ಏನು ಮಾಡಿರಲಿಲ್ಲ ನೀವು. ಆಕ್ಚುಲಿ ಏನು ಹೇಳ್ತದ, ಕ್ಲಾಸಿಕಲ್ ಇಮ್ಯಾಜಿನೇಷನ್ ಆಫ್ ನ್ಯೂಕ್ಲಿಯರ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಬಗ್ಗೆ ಹೇಳ್ತದೆ, ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಬಗ್ಗೆ ಹೇಳ್ತದೆ. ಹೌ ದೋಸ್ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಆರ್ ಅರೇಂಜ್ಡ್ ವಿದಿನ್ ದ ನ್ಯೂಕ್ಲಿಯಸ್ ಅಂತ. ಇದು ಸೆಲ್ ಮಾಡೆಲ್ ಏನು ಹೇಳ್ತದ, ಇಟ್ ಈಸ್ ಆಕ್ಚುಲಿ ಕ್ವಾಂಟಮ್ ಅಸಂಪ್ಷನ್. ಸ್ಪಿನ್ ಅದ, ಆರ್ಬಿಟಲ್ಸ್ ಅದಾವ, ಅದ್ರ ಎಕ್ಸ್ಕ್ಲೂಸಿವ್ ಪ್ರಿನ್ಸಿಪಲ್ ಫಾಲೋ ಮಾಡ್ತೈತಿ. ಹಿಂಗೆ ನಾವು ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. ಅದಕ್ಕೆ ಶೆಲ್ ಮಾಡೆಲ್ ಅನ್ನ ಈ ಮಾಡೆಲ್ಸ್ ಆಗಿ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. ಸೇಮ್ ಶೆಲ್ ಮಾಡೆಲ್ ಅನ್ನ ಕ್ಲಾಸಿಫೈ ಇಂಟು 3 ಡಿಫರೆಂಟ್ ಮಾಡೆಲ್ಸ್. ದಟ್ ಇಸ್ ಸೇಮ್ ಶೆಲ್ ಮಾಡೆಲ್ classified as 3 types, 3 models. 3 model type assumption ಮಾಡ್ಕೊತೀವಿ. One is extreme single particle model. One is extreme single particle model. Single particle model. Another one is single particle, just single particle model. Just single particle model. Particle model. And third one is many particle model. Many particle model. Okay. ಇಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀವಿ, ಸಿಂಗಲ್ ಪಾರ್ಟಿಕಲ್ ಮಾಡೆಲ್ ಒಳಗ ನ್ಯೂಕ್ಲಿಯಸ್ ಇಸ್ ಈಕ್ವಲೆಂಟ್ ಟು ಫಿಲ್ಡ್ ಶೆಲ್ಸ್ ಕೋರ್. ಸೊ ಏನಂತ ಕರಿತೀವಿ ಅಂದ್ರೆ ಫಿಲ್ಡ್ ಶೆಲ್ಸ್ ಕೋರ್ ಅಂತ ಕರಿತೀವಿ. ಹೆಂಗಿರ್ತಾವ ಅಂತಂದ್ರೆ, here nucleus is going to be treated as, here nucleus is going to be treated as, nucleus ಎದಕ್ಕೆ ಈಕ್ವಲೆಂಟ್ ಇರ್ತದಪ್ಪ ಅಂತಂದ್ರೆ, ನೋಡ್ರಿ ಇಲ್ಲಿರುವಂತ ಫಿಲ್ಡ್ ಶೆಲ್ಸ್ ಗಳು ಏನಾಗಿರ್ತಾವ, ಫಿಲ್ಡ್ ಆಗಿರ್ತಾವ. ಫಿಲ್ಡ್ ಶೆಲ್ಸ್ ಕೋರ್ ಜೊತೆಗೆ ಲಾಸ್ಟ್ ಅನ್ಪೇರ್ಡ್ ಎಲೆಕ್ಟ್ರಾನ್, not electrons, this is nucleons. Last unpaired nucleon. ಇವೆರಡೂ ಕೂಡ ಏನ್ ಮಾಡ್ತಾವ ಗೊತ್ತಾ, ಶೆಲ್ಲದ ಪ್ರಾಪರ್ಟಿನ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತಾವ, ನ್ಯೂಕ್ಲಿಯಸ್ ಪ್ರಾಪರ್ಟಿನ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತಾವ. ಇಲ್ಲಿ ಎಕ್ಸ್ಟ್ರೀಮ್ ಸಿಂಗಲ್ ಪಾರ್ಟಿಕಲ್ ಮಾಡಲ್ ನೆಕ್ಸ್ಟ್ ಹೇಳ್ತೀನಿ, ನಾವು ಮಾರ್ನಿಂಗ್ ಅದ ಮಾಡ್ಬೋದು. ನೆಕ್ಸ್ಟ್ ಸಿಂಗಲ್ ಪಾರ್ಟಿಕಲ್ ಮಾಡಲ್ ಅಲ್ಲಿ ಏನಾಗ್ತಾವ ಅಂತಂದ್ರೆ, ಅದೇ ಶೆಲ್ದಾಗಿರುವಂತ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಎಲ್ಲ ಲೂಸ್ಲಿ ಬೌಂಡ್ ಇರ್ತಾವ. ಅದೇ ಮೇನ್ ಲೂಸ್ property. Here also filled shell cores irtav, shells core irtav. ಇಲ್ಲಿ ಕೂಡ filled shells core. Here also all the shells will be filled shells core ಇರುತ್ತೆ. ಅದ್ರ ಜೊತೆಗೆ ಈ ಶೆಲ್ ಆಗಿರುವಂತ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಏನಾಗ್ತಾವ, ಈ ಶೆಲ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಆರ್ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್. They are loose, very loosely bound ಆಗಿರ್ತವೆ. ಇದು ಕೂಡ ಏನ್ ಮಾಡ್ತದೆ, ಅದ್ರ ಪ್ರಾಪರ್ಟಿಯನ್ನು ಹೇಳ್ತದೆ ನ್ಯೂಕ್ಲಿಯಸ್. ದೆನ್ ಇಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀವಿ ಅಂತಂದ್ರೆ, all nucleons contribute ಪ್ರಾಪರ್ಟಿ ಆಫ್ ದ ನ್ಯೂಕ್ಲಿಯಸ್. ಎಲ್ಲಾನು ಕೂಡ ಏನ್ ಮಾಡ್ತತಿ, ನ್ಯೂಕ್ಲಿಯಸ್ ಅನ್ನು ಡಿಫೈನ್ ಮಾಡ್ತದೆ. ಕಾಂಟ್ರಿಬ್ಯೂಟ್ ಪ್ರಾಪರ್ಟಿ ಆಫ್ ದ ನ್ಯೂಕ್ಲಿಯಸ್, ಪ್ರಾಪರ್ಟಿ ಆಫ್ ನ್ಯೂಕ್ಲಿಯಸ್. ಇವೆಲ್ಲ ಏನ್ ಮಾಡ್ತಾವ್ರಿ, ಇಲ್ಲಿ ಮೆನಿ ಪಾರ್ಟಿಕಲ್ ಸಿಸ್ಟಮ್ ಒಳಗಡೆ ಅಷ್ಟು ಕೂಡ ಏನ್ ಮಾಡುತ್ತಾ, ಒಂದು ನ್ಯೂಕ್ಲಿಯಸ್ ಬಗ್ಗೆ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತದೆ. ಬಟ್ ಇಲ್ಲಿ ಹಂಗಲ್ಲ, ಸಿಂಗಲ್ ಪಾರ್ಟಿಕಲ್ ಸಿಸ್ಟಮ್ ಒಳಗಡೆ ಫಿಲ್ಡ್ ಶೆಲ್ಸ್ ಕೋರ್ ಇರ್ತೈತೆ, ಅದ್ರ ಜೊತೆಗೆ ಶೆಲ್ ಒಳಗಡೆ ಇರುವಂತಹ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಕೂಡ ಡಿಫೈನ್ ಮಾಡ್ತವೆ. ಬಟ್ ಇಲ್ಲಿ ಲಾಸ್ ಅನ್ಪೇರ್ಡ್ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಹಿಡ್ಕೊಂಡು ಏನು ಫಿಲ್ಡ್ ಕೋರ್ಸ್ ಏನಿರ್ತವೆ ಅಷ್ಟು ಕೂಡ ನ್ಯೂಕ್ಲಿಯಸ್ ಅನ್ನ ಡಿಫೈನ್ ಮಾಡ್ತವೆ. ಇಲ್ಲಿ ಹಂಗಂತದೇ ಡಿಫೈನ್ ಮಾಡೋದು ಏನಂತದೇನು ಪರ್ಟಿಕ್ಯುಲರ್ಲಿ ಇದು ಹೆಸರು ಮೇಲೆ ಏನಿಲ್ಲ. ಬಟ್ ಅಲ್ಲಿ ಏನಿರ್ತದ ಅಂತ, ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ಗಳು ಹೆಂಗ್ ಪೇರ್ ಆಗ್ಯಾವ, ಅದ್ರ ಸ್ಪಿನ್ ಏನು, ಇದು ಪರ್ಟಿಕ್ಯುಲರ್ಲಿ ಸ್ಪಿನ್ ಪ್ಯಾರಿಟಿ ಅಂತ ಕರಿತೀವಿ. ಸ್ಪಿನ್ ಪ್ಯಾರಿಟಿ, ಒನ್ ಪ್ಯಾರಿಟಿ ಅಂತ ಬರ್ತದೆ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಬಗ್ಗೆ ನಿಮ್ಗೆ ಗೊತ್ತು. ಹಿಯರ್ ಆಲ್ಸೋ we are going to define orbital angular momentum G. After that ಎಷ್ಟು ಎಲೆಕ್ಟ್ರಿಕಲ್ ಪ್ರಾಪರ್ಟಿಗೆ ರೆಸ್ಪಾನ್ಸ್ ಮಾಡ್ತಾವ, ಅಂದ್ರೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಪ್ರಾಪರ್ಟಿಗೆ ಎಷ್ಟು ರೆಸ್ಪಾನ್ಸ್ ಮಾಡ್ತಾವ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಮೂವ್ಮೆಂಟ್ ಬರ್ತೈತಿ. ಇನ್ನೊಂದು ಲ್ಯಾಂಡೇಜ್ ಫ್ಯಾಕ್ಟರ್ ಅಂತ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. ಆ ಟೋಟಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಮೂವ್ಮೆಂಟ್ಗೆ ಇಂಟ್ರಿನ್ಸಿಕ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಮೂವ್ಮೆಂಟ್ ಹೆಂಗ್ ಬರ್ತೈತಿ, ಇಂಟ್ರಿನ್ಸಿಕ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಮೂವ್ಮೆಂಟ್, ಆರ್ಬಿಟಲ್ ಆಂಗುಲರ್ ಮೂವ್ಮೆಂಟ್ ಹೆಂಗ್ ಬರ್ತದ, ಸ್ಪಿನ್ ಆಂಗುಲರ್ ಮೂವ್ಮೆಂಟ್ ಹೆಂಗ್ ಬರ್ತೈತಿ, ಎಲೆಕ್ಟ್ರಿಕಲ್ ಕ್ವಾಡ್ರಪಲ್ ಮೂವ್ಮೆಂಟ್ ಹೆಂಗ್ ಬರುತ್ತೆ, ಅಷ್ಟು ಕೂಡ ಕೌಂಟ್ ಆಗುತ್ತೆ. ಸೊ ನಾಳೆ ಮಾರ್ನಿಂಗ್ ಕ್ಲಾಸ್ ಒಳಗೆ ಏನು ಮಾಡ್ತಾ ಇದೇ ಪಾಯಿಂಟ್ ನೆಕ್ಸ್ಟ್ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ. ಸ್ವಲ್ಪ ಕ್ವಾಂಟಮ್ ಮಾಡೆಲ್ಸ್ಗಳನ್ನ ಇನ್ವಾಲ್ವ್ ಮಾಡ್ಕೋತೀವಿ. ಸ್ಪಿನ್ ಆರ್ಬಿಟಲ್ ಇಂಟ್ರಾಕ್ಷನ್ ಟರ್ಮ್ ಅಂತ ಹೇಳ್ತೀವಿ ಅದಕ್ಕೆ. ಇನ್ನು ಎನರ್ಜಿಗಳು ಡಿಫೈನ್ ಮಾಡ್ಕೋತೀವಿ. ಆಮೇಲೆ ಮ್ಯಾಜಿಕ್ ನಂಬರ್ ಅಂದ್ರೆ ಏನು, ಮ್ಯಾಜಿಕ್ ನಂಬರ್ ಇದ್ದಾಗ ನ್ಯೂಕ್ಲಿಯಸ್ ಅದಕ್ಕೆ ಸ್ಟೇಬಲ್ ಇರ್ತೈತಿ. ಇದ ನ್ಯೂಕ್ಲಿಯಸ್ ಫೀಲ್ಡ್ ಅನ್ನ ಎರಡು ಫೀಲ್ಡ್ ಆಗಿ ತಗೋತೀವಿ. ಒಂದು ಸ್ಕ್ವೇರ್ ವೆಲ್ ಪೊಟೆನ್ಷಿಯಲ್, ಆಲ್ರೆಡಿ ಗೊತ್ತದ, ಇಲ್ಲೊಂದು ಪಾಯಿಂಟ್ ಹೇಳಿದೆ, ಏನಂತ ಹೇಳಿದೆ ನೋಡ್ರಿ, all the particles of the nucleon, each nucleon move in a average field. ಈ ಫೀಲ್ಡ್ ಹೆಂಗದ, ಅದು ಪೊಟೆನ್ಷಿಯಲ್ ಅನ್ನ, ಫೀಲ್ಡ್ ಇಸ್ ನಥಿಂಗ್ ಲೈಕ್ ಅ ಪೊಟೆನ್ಷಿಯಲ್. ಪೊಟೆನ್ಷಿಯಲ್ ಏನು ಸ್ಕ್ವೇರ್ ವೆಲ್ ಪೊಟೆನ್ಷಿಯಲ್ ಅದನ್ನು ಅಥವಾ ಹಾರ್ಮೋನಿಕ್ ಪೊಟೆನ್ಷಿಯಲ್ ಅದನ್ನು. ಸ್ಕ್ವೇರ್ ವೆಲ್ ಪೊಟೆನ್ಷಿಯಲ್ ಇದ್ದ ಪಾರ್ಟಿಕಲ್ಸ್ ಗಳು ಹೆಂಗೆ ಬಿಹೇವ್ ಮಾಡ್ತಾವ, ಹಾರ್ಮೋನಿಕ್ ಆಸಿಲೇಟರ್ ಟೈಪ್ ಇತ್ತಂದ್ರೆ ಅವಾಗ ಹೆಂಗೆ ಬಿಹೇವ್ ಮಾಡ್ತಾವ. ಸೊ ದಟ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಡಿಸ್ಕಸ್ ಇನ್ ದ ಟುಮಾರೋಸ್ ಕ್ಲಾಸ್. ನೆಕ್ಸ್ಟ್ ಅಸಂಪ್ಷನ್ಸ್ ಸೆಕ್ಟರ್ ನೆನ್ಪಿಟ್ಕೋರಿ. ಅಸಂಪ್ಷನ್ಸ್ ಬೇಸ್ ಮೇಲೆ ದಟ್ ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ಇಂಟ್ರೊಡ್ಯೂಸ್ ಶೆಲ್ ಮಾಡೆಲಿಂಗ್ by treating Schrodinger wave equation, eigen value equation of the shell model. ಇಟ್ಕೊಂಡು ನಾನು ಮಾರ್ನಿಂಗ್ ಕ್ಲಾಸ್ ಒಳಗಡೆ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತೀನಿ. ವೆದರ್ ಇಟ್ ಇಸ್ ಸ್ಕ್ವೇರ್ ಬಾಕ್ಸ್ ಇದ್ದಾಗ ಹೆಂಗಿರ್ತದೆ, ಹಾರ್ಮೋನಿಕ್ ಆಸಿಲೇಟರ್ ಇದ್ದಾಗ ಹೆಂಗಿರ್ತದೆ. ಓಕೆ, ಸೊ ನಾನು ಶೆಲ್ ಮಾಡೆಲ್ ನಾನು ಮಾರ್ನಿಂಗ್ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತೀನಿ. ಟೈಮ್ ಆಯ್ತು.